When determining the appropriate size for a neutral conductor in a 480 volts, 100 amp circuit, the National Electrical Code provides specific guidelines. A key principle is that the neutral conductor must be at least one-half the size of the feeder conductors. However, the NEC also establishes minimum size requirements that must be met regardless of the calculation based on the feeder conductors. The minimum size of the neutral is not smaller than 1/0 AWG copper or 300 kc mil aluminum. Applying these rules to the case of a 480 volts, 100 amp circuit, let's consider the following. Suppose the feeder conductors are sized at 2 AWG copper. According to the rule that the neutral conductor must be at least one-half the size of the feeder conductors, a conductor of one size less could be acceptable. However, you must ensure that the neutral is rated to carry the expected neutral current. To determine the proper neutral size, you should conduct a load calculation. This calculation will determine the maximum current that the neutral conductor is expected to carry. This is particularly important for circuits that serve nonlinear loads. Nonlinear loads such as LED drivers, variable frequency drives, and electronic ballast can cause harmonic currents to flow in the neutral conductor. These harmonic currents can significantly increase the current flowing in the neutral, potentially overloading undersized conductors. In situations where harmonic currents are present, it is often necessary to increase the size of the neutral conductor to accommodate the increased current flow. In some cases, the NEC may require the neutral conductor to be the same size as the phase conductors to account for harmonic currents. If the load calculation dictates that the neutral current will be 50 amps or less, then a 2 AWG copper conductor or a 4 AWG aluminum conductor would be acceptable, as it meets the minimum size requirement of at least one-half the size of the feeder conductors. Also, the 2 AWG copper or 4 AWG aluminum is not smaller than the minimum 1/0 AWG copper or 300 kc mil aluminum. Remember that it is always the electrician's responsibility to ensure that all wiring is compliant with the latest version of the NEC and all local codes. Consult with a qualified electrical engineer if you have any doubts about the correct size of the neutral conductor for your application. The NEC provides tables, such as Table 310.16, which specify the allowable ampacities of conductors based on their size and insulation type. It is essential to select a conductor size that has an ampacity rating equal to or greater than the calculated neutral current. Furthermore, derating factors must be considered when conductors are installed in environments with high ambient temperatures or when multiple conductors are bundled together. Derating factors reduce the allowable ampacity of conductors and must be applied to ensure that the conductors are not overloaded. The selection of the appropriate insulation type is also crucial. Different insulation types have different temperature ratings, and it is essential to select an insulation type that is suitable for the environment in which the conductor will be installed. For example, conductors installed in high-temperature environments will require insulation with a higher temperature rating. The length of the circuit also plays a role in determining the appropriate conductor size. Longer circuits will experience greater voltage drop, which can affect the performance of the equipment being powered. To minimize voltage drop, it may be necessary to increase the size of the conductors. Voltage drop calculations should be performed to ensure that the voltage at the equipment is within the acceptable range. Grounding is another critical aspect of electrical safety. The grounding system provides a low impedance path for fault current to flow back to the source, which helps to protect equipment and personnel from electrical shock. The grounding conductor must be properly sized and installed to ensure that it can effectively carry fault current. In addition to the NEC, other standards and regulations may apply to electrical installations. These standards may be specific to certain industries or applications. It is essential to be familiar with all applicable standards and regulations to ensure that the electrical installation is safe and compliant. Proper labeling of electrical panels and circuits is also crucial for safety. Clearer and accurate labels help to identify circuits and prevent accidental energization of the wrong equipment. Labels should be durable and easy to read, and they should be updated whenever changes are made to the electrical system. Regular inspection and maintenance of electrical systems are essential to ensure their continued safety and reliability. Inspection should be performed by qualified personnel, and any identified problems should be promptly corrected. Maintenance activities should include tightening connections, cleaning equipment, and testing protective devices. A well-maintained electrical system is less likely to experience failures or create safety hazards. Continuous education and training are essential for electrical professionals. The electrical industry is constantly evolving, and it is important to stay up to date on the latest codes, standards, and technologies. Continuous education helps to ensure that electrical professionals have the knowledge and skills necessary to perform their job safely and effectively. In summary, determining the proper size of a neutral conductor for a 480 volts, 100 amp circuit requires careful consideration of the NEC, load calculations, and other factors. It is essential to consult with a qualified electrical engineer if you have any doubts about the correct size of the neutral conductor for your application. Remember that safety should always be the top priority when working with electricity. Adhering to the NEC and other applicable standards and regulations is crucial for protecting people and property from electrical hazards. Firstly, the neutral conductor must be at least 1/2 the size of the feeder conductors. Secondly, the minimum size is 1/0 AWG copper or 300 kc mil aluminum. Thirdly, load calculations are essential, especially for circuits with nonlinear loads. Fourthly, consider the ampacity rating of the conductor. Fifthly, directing factors for temperature and bundling must be accounted for. Sixthly, select the appropriate insulation type. Seventhly, consider the length of the circuit for voltage drop. Eighthly, ensure proper grounding. Ninthly, adhere to all applicable standards and regulations. Tenthly, maintain proper labeling of electrical panels and circuits. 11thly, ensure regular inspection and maintenance of electrical systems. And 12thly, engage in continuous education and training to stay updated on the latest codes and technologies. The complexities of electrical systems demand a comprehensive approach to safety and compliance. Consulting with experienced professionals, staying informed about code updates, and implementing thorough maintenance practices will contribute to a safer electrical environment. It's important to be aware of the increasing prevalence of nonlinear loads in modern electrical systems. These loads, such as those found in electronic devices and LED lighting, generate harmonic currents that can significantly impact the neutral conductor. Harmonic currents are multiples of the fundamental frequency of the power supply, typically 60 Hz in the United States. These harmonic currents can cause the neutral conductor to overheat, leading to insulation damage and potential fire hazards. In some cases, the NEC requires the neutral conductor to be oversized to accommodate harmonic currents. The degree of oversizing depends on the percentage of nonlinear loads in the circuit. For example, if a circuit has a high percentage of nonlinear loads, the NEC may require the neutral conductor to be the same size as the phase conductors. It's also essential to consider the impact of voltage imbalances on the neutral conductor. Voltage imbalances can occur when the loads and the three phases of a three-phase system are not evenly distributed. Voltage imbalances can cause increased current flow in the neutral conductor, leading to overheating and potential damage. To minimize voltage imbalances, it's important to distribute loads evenly across the three phases. Regular monitoring of voltage levels can help to identify and correct voltage imbalances. Surge protection is another important aspect of electrical safety. Surges can damage sensitive electronic equipment and even cause fires. Surge protective devices should be installed at the service entrance and at individual pieces of equipment to protect against surges. The size and type of surge protective device should be selected based on the specific application and the level of surge protection required. Arc flash is a dangerous phenomenon that can occur when there is a fault in an electrical system. Arc flash can generate intense heat and pressure, causing serious burns and other injuries. To protect against arc flash hazards, it's important to wear appropriate personal protective equipment such as flame-resistant clothing and arc-rated face shields. Arc flash studies can be conducted to determine the potential arc flash hazard levels in a particular electrical system. Based on the results of the arc flash study, appropriate safety measures can be implemented to reduce the risk of arc flash injuries. In addition to the technical aspects of electrical safety, it's also important to focus on human factors. Human error is a leading cause of electrical accidents. To reduce the risk of human error, it's important to provide adequate training and supervision to electrical workers. Safety procedures should be clearly defined and consistently followed. It's also important to foster a culture of safety in the workplace, where workers are encouraged to report hazards and near misses. The NEC is updated every 3 years to reflect changes in technology and industry practices. It's important for electrical professionals to stay up to date on the latest NEC requirements. Continuing education courses and industry publications can help electrical professionals stay informed about the latest changes in the NEC. The NEC is not a design manual, but it provides minimum requirements for electrical safety. It's important to consider the specific application and the overall system design when making electrical design decisions. In some cases, it may be necessary to exceed the minimum requirements of the NEC to ensure a safe and reliable electrical system. Electrical safety is a shared responsibility. Everyone who works with electricity should be aware of the hazards and take steps to protect themselves and others. By following safe work practices and adhering to the NEC, we can help to prevent electrical accidents and injuries. The information provided is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical engineer or electrician before making any electrical design or installation decisions. It's important to remember that electrical codes and regulations can vary depending on the location. Always check with the local authorities to ensure that your electrical work complies with all applicable codes and regulations. The use of high-quality electrical components is essential for ensuring the safety and reliability of electrical systems. Cheap or substandard components can fail prematurely or create safety hazards. It's important to select electrical components from reputable manufacturers and to ensure that they are properly rated for the intended application. Proper installation techniques are also crucial for electrical safety. Improperly installed electrical components can create hazards such as loose connections, exposed wires, and damaged insulation. It's important to follow the manufacturer's instructions carefully when installing electrical components. Regular testing of electrical systems can help to identify potential problems before they lead to failures or safety hazards. Testing should be performed by qualified personnel using appropriate test equipment. Testing can include insulation resistance testing, ground resistance testing, and circuit breaker testing. The results of the testing should be documented and used to identify areas that need attention. Electrical systems should be protected from physical damage. Conduit should be used to protect wires from abrasion and impact. Electrical panels should be located in areas where they are not likely to be damaged. Equipment should be properly secured to prevent it from falling or tipping over. Electrical systems should be protected from moisture. Moisture can cause corrosion and can create electrical shock hazards. Electrical equipment should be located in dry areas and should be protected from rain and snow. Ceiling fittings should be used to prevent moisture from entering conduit. Electrical systems should be protected from overcurrent. Overcurrent can cause wires to overheat and can lead to fires. Circuit breakers and fuses should be used to protect circuits from overcurrent. The size of the circuit breaker or fuse should be selected based on the ampacity of the wires in the circuit. The electrical system should be properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electrical shock. The grounding system should be properly designed and installed. The grounding electrode should be connected to the earth. Electrical systems should be properly bonded. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current to flow. Bonding helps to prevent voltage differences between metal parts, which can cause electrical shock hazards.